So I start again. I will talk a little about the balancing challenges more in detail. I think this we have already talked about. Then I will take this as a small example. This is basics from power system point of view, but I will go through it a little and talk a little about how it works. What is happening here is the following. It's a very small system here, and we have the consumption, and then we have a production plant here, and exactly when this stops, like this, the question is, where do we get the power from? And the power we in reality get from the rotating energy from the synchronous machines. This is the primary control. I think you hopefully have studied it, but just to repeat a little like this. We have a synchronous machine here with a turbine here. We have the shaft here, which is rotating shaft. And then we have here in reality a rotor. And here we have the stator of the machine. And then we have connection to the grid. And here we are sending in a certain amount of power, which is called the P, the mechanical part. And then we are sending out something here called the electric power here. And then, just to simplify it, we have a house here that is consuming power, or a town or something, and then we have a power generation here which is producing 30 megawatt. Just to make it simple, we say that this one is consuming 70. That means that you here get 40, and then we assume that you also get 40. Try this. Okay, what happens here? That suddenly this one stops. Stopped. But remember, we still have an electric system, and if I'm consuming 70, of course I will get exactly a millisecond, I will get 70. So plus, suddenly, you get plus 30 here instead. And this is the fundamental issue of synchronous machines, that they deliver this extra 30 megawatt here. But you still have 40 here. So where does this 30 come from? It comes from here. P, inertia, plus 30. And of course, you have something, a heavy thing. With this, it's rather heavy. It's a long shaft. It's metal and so on. You have a turbine connected to it and so on. You have the rotor here. So, of course, it can turn around. And on the other hand, if you take out inertia from it, what happens is then that it starts to run slower. So if this one is rotating slower, then, of course, the frequency will decrease here. So if you take out inertia, the frequency will go down. And that is exactly what happens. The frequency, suddenly you use the inertia like this, toof, and then this is in really a wrong order, because then what happens is that the frequency starts to decrease. I will take more details than if you go into dynamics. The frequency starts to decrease, and then you do the following, and that is your nice control system, is that you here measure frequency, control P, mechanical. And that is your primary control. And that is what is happening here, that the grid frequency decreases, and when the grid frequency decreases, then the production is increasing like this. The important thing is that since we have, for example, the same frequency in the whole India, this means that if you do something here, it is in reality compensated in India, not in Allahabad, in India. And that is, of course, changing the transmission on all lines and so on. And this is, let's say, really the fundamental issue of how to handle this. There are then some challenges if you have wind power. Where is the inertia? Because this is really the big fundamental issue. If you have a huge amount, this whole control system, that means that the power system is working, is based on that you have inertia in this kind of power plants. What is happening is, of course, that if these don't exist, or you have very few of this one, then the frequency, when something happens in the system, and that is one of the challenges that is very much discussed today, how to handle that. One idea, I talked about it earlier, is if you do the following. I can illustrate it with the same figure. One possibility is, for example, if you have gas turbines, there are gas turbines today where you can disconnect the rotor from the turbine mechanically. So then you can run this with only this part. And then, and the reason why you do it is the following. This turbine, I don't know if you have seen a big turbine, but if you're, let's say if you don't disconnect this, if this one is rotating and you are not producing in this kind of turbine, this will more or less look like a fan that is consuming a huge amount of power if you run it in air. If you have a hydropower plant, that we have in Sweden, we have sometimes hydropower plants that are running in the air, because then you can just put on water and then you start to produce a lot. But if you have a gas turbine of some kind, then this is more, if you see because there's the air is is going, steam turbine, the steam is going through it, and then you make it rotate. And if you don't have the steam and you want this to rotate, then you are in reality moving air instead. So then if you just have this rotating in the air, then of course it will consume a huge amount of power because it's a big fan, which is not the idea. So because of that, if you have a gas turbine and you want to use it as only a synchronous machine, then you have to disconnect it here. This is technically possible, and that is, as I talked about that earlier, they are doing that, for example, in North Chicago. They have done that. They took an old nuclear power plant and then they disconnected the turbine. The problem is that then you get significantly lower inertia because you took away a lot of the heavy part. This is in reality the H that you have in the, and the H variable is in reality decreasing a lot if you take away the turbine. So let's say this is the fundamental issue, that the question is how fast this frequency decreases. And then that depends also on what you have here. I will show you some examples in a while. I will just take my thing, which I'm using rather often. The power system is a long bike. This is just because this is mainly for students who perhaps already know all things, but from my point of view, this is an important issue. If you have a bike like this, everyone is having the same speed. Remember that on this bike. Never know, and this guy here, he's the system operator. He's looking here on the speed, and his aim is to keep a constant speed. And what is important is that if this guy starts to bike a lot, the bike will not go faster because he's keeping the speed. So if he's biking a lot, he is in reality decreasing his speed. If he starts to braking, or if he's braking his legs, you still have, since he's keeping the speed, everyone here, no matter if they are braking or they are biking, they will have the same speed. Everyone in India is sitting on the same bike. So in a bike, you can say the bike balance is that the pedal forces is equal to the braking forces, otherwise you get a changed speed. So if you want to, okay, now something has happened here, I see. In the power system, the total generation is equal to total load. And then I say otherwise here, because now I'm talking about the difference between, not in the electric system, you always have exact balance, but in the mechanical system, you not always have the balance. Here is you are consuming 70, but in the initial part, what happened in the beginning was that you only produced 40. So here you can have an imbalance. On the mechanical side, from the mechanical power to the electric power, you can have an imbalance, but you can never have an imbalance here. Here you have always that the consumption, including losses, is exactly equal to the production. So this, that you have an exact balance, is in the electric system, not necessarily here, because here you have some storage, and that is what you have there. So the aim on the bike is to keep a constant speed and measure the speed, which is the same on the whole bike. And that is the important thing, that if the speed goes down, then everyone here can check the speed. And they know the speed, they know the speed, they know the speed. And perhaps you have told everyone here, if the speed goes down, can you please start the bike a bit more? Then everyone is participating in the speed control, which is in reality what you normally have in the power system, that everyone is, the big power plants are participating in the frequency control. Oh, I destroyed, this is, now it's not perfect. So you are measuring, the aim on the power system is to keep a constant frequency and to measure the frequency. Because what is good in the power system, if the frequency is constant, if you have a constant frequency in the power system, then you are not taking out energy and energy here. Because if you are taking out, if the frequency is decreasing, then you are using the inertia in the system. On the other hand, if the frequency is increasing, then you are in reality putting in more power here than you are taking out here. So this is the, let's say, the fundamental issue of a frequency control in the power system. Just assume, if you look on these guys here, the total weight here is probably around 1 ton, I think, because you have, I think it's 10 persons here. No, it's 12 persons on this bike, probably 80 kilo each, at least, if you look here. And then so it's probably a ton, and then you have the weight of the bike, so it's 1.2, 1.3 tons, probably. And if you suddenly brake here, then will the bike stop immediately? Of course not. And that has to do with the inertia. So you have a significant inertia on this bike. It's 1.3 ton. On the other hand, assume that these were slim guys, only weight 1 kilo each, and then you have the plastic bike, and someone starts to brake. What happens? And this is exactly the inertia problem you have in the power system, that you need inertia, otherwise any changes will keep rapid changes in the frequency in the power system. So now back to this one. That is exactly what is happening in this one. So now we go into a bit more detail. As I said, this is very simplified, just to get the feeling about how it's working. The frequency, you have an outage, or you can say that suddenly a connection to your solar farm, you have a 30 megawatt wind solar farm, and there was a disconnection in the grid. So you lost your 30 megawatt solar power here. So it's the same thing. It doesn't matter if it's wind or solar or anything. You have a change in the system. It can be a change to demand. I mean, I think an important thing, let's say you take this guy here. If he says you change speed, he doesn't know anything. If it's this guy that is only biking when it's sunny and it came a cloud, this guy is only biking when it's windy, and this guy, he broke his legs, and this guy here, he's suddenly tried to bike a bit more, and this guy started to brake. This guy doesn't know anything. He only sees the speed of the bike. And that is the important thing, that from the balancing point of view in the system, everything is lumped together, and we are sitting on the same bike in the Nordic system, and you are sitting on the same bike in the India. So this is the Indian bike. I have a paper on this in IEEE around 10, 15 years ago. You can also have reactive power here. That is the question, is where you are sitting on the bike, if you are sitting there or you are sitting there. And then you have to balance, otherwise the bike will fall. Okay. This is more close to reality. This is an outage in a Swedish, not an out, yes, an outage in a Swedish nuclear power station. So this is how it looks in reality. That you have, that this is the frequency